Hello everyone, my name's Paul Newman. I am founder and CTO of Oxbotica. We are an Oxford and Toronto based autonomy company. We're a software company and we've got a big vision, and it's to change the way that goods and people are moved. So it's a big ask, and we're doing well. And here's the vision. This is the only equation I'm going to put in the slides, okay? But this is something I wrote down when I was back in MIT in about 2002. And it was, what am I doing with my life? And I wrote X to infinity and T to infinity down. Now, what I mean by that is I want vehicles to be able to work everywhere. So that's X. And I want them to work for all time. So that's T to infinity. And pretty much everything that I've done since then and everything this company has done has been about that. Because if we can get X to infinity and T to infinity, we can work for any industry. And autonomy is going to turn up in many industries. It's not a thing that's just owned by the roads. In fact, you know, ports have been autonomous for 20 years now. So I really want vehicles in all places at all time to be autonomous. And then we can apply that to any industry. So to do that, there's you've got to be careful, and you've got to try and build one stack for all of it. So I'm hoping that these videos are playing-ish okay. It's Zoom was designed to send pictures of skulls with skin on it, not pictures of autonomy working in different places. But these videos here, these 4 videos, are exactly the same software stack running in very different environments. There's no change. At the top left, this was us doing passengers in London last year. At the top right, that's going cross country there. At the bottom left, that's in a mine in Australia. And at the bottom right, that's doing some delivery with Ocado a few years ago. And what I would stress here is that none of this is using things like GPS. This is all using just onboard sensors, cameras, laser, radar, very low compute. So we're at about 300 to 400 watts for the compute there. And of course, perception is a major part of that. And part of this system, of course, is AI. And that's what we're going to be talking about today. And in particular, I think I'm going to talk about the data problem in feeding these AI components. But the message from this slide is, this is all the same problem, because you need to answer these. I used to say there are 3 questions, but now I think there are 4 or 5. So you need to be able to answer, where am I? I need to do that everywhere and anywhere, any time of the day. And that doesn't mean you should be using a GPS, because that certainly won't work in a mine, and it certainly won't work underground. You need to answer what surrounds me. So what stuff is around me? Is that a person? Is that a car? Is it a truck? Is it an obstacle in the road? What is it? And then the really thorny one. Okay, so if I know where I am and what's around me, what's going to happen next? Like, so predicting the future. And that's the monster problem in AVs. And then what do I do? Because if I know where I am, I know what's around me, and I've got an idea of predicting what's going to happen next, I can make a plan. And then the 5th one is, what am I going to share? Now, each of these pillars of autonomy are built from multiple techniques. No one technique owns the lot. So where am I is a combination of optimization and machine learning. And what surrounds me is a combination of optimization and machine learning. I'm not saying that machine learning isn't a form of optimization. Of course it is, but I think people understand the differentiation I'm making. What happens next? Again, optimization, machine learning, and what do I do? Optimization and machine learning. And what do I share? Well, that probably is not so much optimization, but that's an ML. So where is novelty? What would the rest of the fleet want to know? So we have got some monster tough problems ahead of us in cracking this problem. So we're going to be compelled and required, and we should have audit and explainability in our systems. So we must post-event be able to give a sense of transparency of the intent of what a vehicle, be that a forklift, a mining vehicle, a delivery vehicle on your pavement, or a robot taxi. We must be able to explain why a vehicle did something. That has to be done post hoc. So things fail when working correctly. That's a very different thing as well. So we're going to have to build systems that, when they're working correctly, give the wrong answer. Right? So that's the probabilistic nature of AI. So put very simply, sometimes Let me give you an example. You might be tracking a cyclist, and occasionally it says that's just a person because their feet are down and they've just stood by the side of the road. So the network's working correctly there, but it's giving the wrong answer. So how are we going to design systems that can work like that? And of course, safety of the intended function comes into that as well. I won't be talking about the first two in the remaining 15 minutes, but I will be talking about ways to get hold of data sources. So if we're going to be training AIs up, as certainly we will, there are some really like sort of three sort of big problems that we've got. We can't wait forever to be shown the tricky event, right? So rare events are rare, right? And it's the rare things that are going to catch us out. So you can't sit around waiting for a rare thing to happen because it's rare. So somehow we're going to have to get our AI's experience of the unusual things. And we can't wait for that. So how are we going to do that? I think that lifelong learning is imperative. I'm not in the school that says there's going to be a release and that's how the system's going to work for the next 2 to 3 years. We will be compelled to share the learnings across vehicles because one vehicle saw something odd, right, that could be learned from, and really we must be explaining and sharing that knowledge across a fleet. So that's going to be important about how are we going to have the provenance and how are we going to have audit of the data sources that we are sharing across fleets of vehicles, irrespective of their domain. And then I think something interesting happens. You could then start to think about, well, do I actually want to make something that's everywhere mediocre? Or are these vehicles likely to work in the first instances in certain places? So let's take a mining vehicle. It's going to work in that mine probably for many years. A delivery vehicle probably will be located in a city for many years. A shuttle will probably be located in that particular shuttle for many years. Forklifts probably stay in that warehouse for many years. So there's an opportunity here for these systems to become local experts. And again, that's a data source, a management and data acquisition issue that I think is interesting. So that's what I'm going to talk about in a few minutes to remain. So let's talk about some of those data sources. So here's the vanilla way to do this, and I'm hoping this is playing okay. So here is something called instance segmentation and depth completion, working off a visual camera. On the right hand side there, you can see that it's spotting and putting boxes around vehicles and humans. This is per frame by frame. It's not showing the smooth version. This, by the way, is working on under 30 watts. And the data source for this was a human sitting and labeling a couple of thousand pictures. Very, very few pictures, but it is quite expensive to do. And you really can get quite good performances, but I don't think it scales amazingly well. I really don't want to be spending any money on having a human labeling things, but this is perhaps what you would expect to get from a very good AI driving off a camera. And at the bottom there, it's doing some depth completion by using a sparse laser with the camera, and we're actually tracking things at distances around. So that's the vanilla approach to acquiring data, is that you might ask humans. In fact, we have a Python script, human.do, that dispatches some images, and a few days later, a few pictures come back that have been carefully labeled, and that produces the curriculum for the vehicle. So that's what you'd expect to see. There's something smarter that maybe you can do in some cases. And here we're teaching the machine to spot traffic lights. Now, because we know where we are so well in the world by using computer vision, we can predict on this route where those traffic lights are going to be. And those green boxes that you're seeing across the bottom there, those are boxes drawn because the vehicle knows where it is by using computer vision so well. I can predict that in those boxes, I'm going to see traffic lights. And so the training data then can appear at the top. Okay, and each of those is a picture potentially of a traffic light in a different state at different distances. So we're allowed now, in fact, we're actually showing the inference working here. We're spotting traffic lights out at 120 meters when they're just a few pixels high, because we're able to get the sort of training data that would be very hard to get by hand labeling. So in this sense, we're using sort of the fact that we can answer where am I to teach us how to answer what's around me. And that's kind of a self-labeling source that's kind of cute. The next way you might think about doing this is, let's build a simulation. So I hope the videos are playing here again. So this is our simulation suite running. Again, this is actually running the autonomy software in the loop. So these vehicles are actually running the software stack here, including the ones at the bottom right there on the mine. So one of the ways you could then do is, if we can script this simulator as we can, and we have a nice open API and it's headless and it can run on the cloud, we could then script the unusual situations and say, well, there's an extraordinary thing and there was a bike and it suddenly flew out between two cars. So we can script those. So that's one of the ways, of course, that we could get at the unusual events. And this scales beautifully. We can have, thousands of these instances running. In fact, they run every time someone checks some code in. So we can get at the unusual events there. So that gives us the unusual scenarios for planning and interactions with vehicles. But what about sensors? Can we simulate sensor data? So it's kind of hard to see this one, but this is us simulating some laser data. That's fairly easy. And the nice thing about this is, because in the simulator we know what the objects are, we can label the laser data. So for example, here, that car, I'm not saying it's red laser light. I'm saying that all the returns that come from that part that's red are all attached to a car. So this is another way. So we can load in a simulation of an environment that we are going to. So we can load in a map of the environment that we're going to, and then we can practice perception in that place and produce training data that's bespoke to that place. To give you some sort of sense, so we can get 11,000 labeled point clouds in half an hour. So that really is quite nice scaling. So some of these sensors are really quite easy to do once you've got this tech going. And I should, we're getting sort of 10–20% increases for no effort in the performance of some of the AI networks, because we augment real data with this synthetic data. And of course, it's now expensive to build the simulator, but free for us to now use internally. So that's quite nice. I've talked about the vanilla case, where you hand label a curriculum and go, by the way, this is a car, this is a person, this is a flamingo, this is an aardvark, this is a trash can. And you build up a lexicon of examples to show an AI at that point. I've then said, well, we can do some of the unusual cases for events and scenarios in simulation. Of course we can, because we can't wait for the odd things to happen because they're odd and rare. And I've said that we can simulate some sensors, like, for example, the laser. But what about photorealism? So I can get lots and lots of photos, but can I generate odd examples from photos? Now, I, at the moment, think it's a little hard to simulate the universe in terms of all photon interactions with all surfaces, to simulate whole surfaces from 3D models. I think that's quite hard. But what you can do, and I'm going to show you here, is if I was given a picture like this, and this is a semantic mask where, and I'll tell you how we can get these, all trees are green, all buildings are yellow, roads are gray, cars are red. That looks like a rubbish picture. But what we can do is think about how we can turn that into something that is quite photorealistic. So, there's a lot of concern, quite rightly, about deep fakes. They're also kind of epic. So the next couple of pictures here are fake. So the ones on the left are synthetic. So the ones on the left there are what we call semantic masks, where all cars are green. And on the right, those images never existed. So they're entirely synthetic, made by one of our AIs. So what we're doing here is we're training a teacher to produce a curriculum, right? So in fact, we're sort of, it's like a teacher training college. We're producing an AI that can produce examples for AIs to learn from. And this, again, takes not many seconds. So if we had one of these images on the left, how might we do that? And of course, this image here that we can come from, the semantic one, that can be generated by the simulator, because I don't need any photorealism. So we can come up with blocky worlds that are about the right shape, which is what 3D simulation is really good at. And I can get the photorealism from one of our AIs doing some deep fake generation. But there's more you can do. What we could do next is we can then manipulate the scene programmatically. So again, we've taken scenes on the left-hand side here that are semantic, and where that arrow is, the left turn, right turn arrow, that's parametric. So we have programmatic control over that guy's location. So we can then flip that guy around and we can generate road scenes that never existed. And that's quite a powerful thing for us as well. So we could take a scene that we've been in, and we can say, what would happen if vehicles were in different places, road markings were in different places, and we can mess around with that to our heart's content. And that's a really lovely, very scalable data augmentation technique using the sensor data that we have. And then you might say, well, okay, that's changed what the appearance of the scene looks like and the structure of it semantically. The next things we can do is say, okay, I'd like to mess around with the lighting. So we can take one of those images and then we can transform that to different lighting conditions. So the photo on the left is from a sensor, a camera sensor, and that's real. And the one on the right is fake. So the one on the right has taken the one on the left and made it look like nighttime. And it's kind of cute, right? It hallucinates things that aren't there. So you can see the one on the bottom with the buses. It's hallucinated there might be street lights in the distance. It's given us a patch of illumination on the ground. And this can be run many times. I could pull the handle again and it will color it in a slightly different way. So again, this is this great data augmentation technique where I can take something and I can expand it to give me a lot of variation in my data. So just to sort of bring this to a close, here are some options that we have. So we can handcraft the curriculum, and that is expensive, very expensive, scales really badly, has humans doing what humans shouldn't be doing, but it's real, right? So it's like, if you like, the gold standard. You could learn by experience, by being out there, and every time you go past the traffic lights, every time you go past something that, you know, the laser says there's a car, you can project that into vision, and you get loads of experiences. So that's slow, but it is relevant. So that is a way to become a local expert. I get to see what that mining truck looks like in that environment. I get to see that delivery vehicle at that rotary, at that roundabout. And so there is something to be done that's very strong about that. And I don't think we have to choose one of these. I think actually we'd use all of these approaches. You can simulate the world. I think it's great in some ways, but I think it gets super awkward if you're going to kid yourself that you can solve Maxwell's equations in real time, such that you can make things super photorealistic. The way that we do it is making it photorealistic by trying to produce fakes that are indistinguishable from a collection of real photos. And then the other thing you could do is you could build a curriculum. So you could build a teacher training college that teaches teachers to produce curriculum for the AI that is realistic. And I think that has a massive amount of scalability. So on a desktop, I can generate 10,000s of images in a couple of hours that are extremely well labeled and produce an amazing diversity. And I can change the weather, I can superimpose rain onto it, and that's all done with it without a human touching it. So I think that's an important part of it as well. And simulation is not a substitution for running it wild in the wild. Okay, so one more slide to go. Let's just be clear though, AI is just a tool, right? And it's just like any other, and I think we need to keep that very, very clear. And it has a giant part to play, but it has to partner with other techniques that are established and still developing: control, optimization, verification. We're not close yet to having a black box, I just drive, I learned how to drive. I think you need to be far more nuanced about it. And our greatest challenges are going to be around the fuel sources for our AI components. The cost of the fuel, how hard it is to make it, the provenance of it, where does it come from? Do I trust this data? And the relevance of that data to the particular ODD in which the vehicle will be running. So are you going to build something that's averagely good everywhere, or are you going to build something that's really, really good for Berlin because you're going to be running it in Berlin? And I think we need to build an ecosystem that allows the vehicles to become local experts, just like vehicle drivers are local experts in their domains. So my last slide is, but this is going to move the sort of fuel and the quality of the fuel that we have, and the way in which we can use these AIs is going to go much faster than vehicle fleets refresh. There'll be a physical vehicle, a bunch of atoms, that is going to change much, much less frequently than the software and the data substrate and the fuel that's going to be running those AIs. So we have got interesting challenges there on validation and verification about that the system is not the same on Friday as on Monday. But I think here's the big point, that we're going to be compelled to share this data. So if something happens to a vehicle in Copenhagen and a learning is made from that, we're going to have to share that with vehicles running in Cape Town as quickly as we can, because we found a way to improve it and it could be shared. And for me, that's the single driving force of why these autonomous vehicles are going to be so extraordinary in all domains is previously, if one driver has an experience, a human driver has an experience, just that one driver gets better. But now we're in a world where one driver, one vehicle has the ability to improve all drivers all the time. So when I get in a vehicle in 5, 10, doesn't matter, many years time, that vehicle will have the benefit of every mile driven by every autonomous vehicle ever. And I think that is the reason we're going to have to share. And data is going to be at the heart of that. So we better start thinking about that. And I'm going to call it a day there. Thank you very much.